I went to a variety of public and parochial schools. I actually had a marvelous opportunity to go to a rather small parochial school, which had 5 or 6 students in a classroom, in one class. And so when we had four classes in one classroom, I had fun because I would try to answer questions with the older kids and work out their stuff. So I went to parochial schools through grade school and then public schools through high school. They encouraged me certainly to do what I wanted to do. It gave us a lot of freedom. My dad was a minister, and my mother was a nurse, and 2 brothers. And I think we had the freedom to do a lot of crazy things. Actually, I remember spilling battery acid on my mother's new carpet once, leaving holes in it. Yeah. But we made chemicals in the lab, too, downstairs in the basement. That was our lab. I made explosives and other things, and that was fun. So they didn't stop us, and they encouraged us. Yeah, I guess I did like school. I don't think that I could say anything other than that, because we had fun in school. It was more than just academics, too. Oh, I think I wanted to go into teaching early on. I thought I wanted to teach the high school level, maybe the grade school level initially. But, of course, I thought about the ministry, obviously. But I moved away from that when I found out there's just so much to learn about our world. Well, I've always been kind of inquisitive of what makes things work in the world, and just asking questions about what's around me. And I suppose I really got some concrete interest in molecular science, chemistry, when I was in high school. We started understanding what spots your clothes, why do you get clothes dirty, and how do you get the stuff out, you know. And that was kind of fun because the person, the dry cleaner I worked for, had no foggy idea of why it worked. But I found out and would try all sorts of things. I think anybody who's done anything in science today has a demonstrated curiosity for the world in which we live. Well, as I said, I was originally interested in education initially, and I moved into the focus on what I can contribute in the scientific realm after I started college. And I realized that in order to really create new knowledge or develop an understanding of the world in which we live, I would have to do more than just teach in this area of activity. And in fact, it wasn't really until I was in college and then graduate school that it became crystal clear that I was going to do scientific research as well as teach. I've had a broad-ranging interest in metal ions and their role. I suppose that first developed pretty early on when I realized that elements like copper can be blue and green and all sorts of things in different compounds, and I didn't understand why, I guess. And cobalt, why is cobalt giving such beautiful blue colors sometimes and pink colors other times? And I think it was that fascination with the metal ions that really started pretty early on. But what I had intended to really understand was radioactivity and nuclear processes of these elements. In fact, before I started graduate school, I had prepped myself to go into radiochemistry, nuclear chemistry, and because Glenn Seaborg and his work at Berkeley had attracted my attention. I'd read a lot of his papers and that sort of things. But things changed quickly in graduate school. About 25, almost 30 years ago now, I guess, one of the graduate students I had said, can we work on some gold chemistry? Because it seems that very little's been done with some of the properties of these gold compounds. And I sort of laughed at him. Why, you know? And I looked into it a little bit, and I quickly realized he was right, that this was prior to the middle 70s. And you recall we went off the gold standard about 1972 or 3. And prior to that time, companies didn't do research with gold because they didn't want the employees walking off with the chemicals. It was money. real money. And so there was very little done prior to the middle 70s in terms of understanding the properties of gold. Some work had been done on gold use as a drug in rheumatoid arthritis in certain compounds, and that was kind of fascinating. No one knew why it worked. Still don't to some extent. But I suppose that was what triggered the interest in this element, and as we delved into it a little more deeply, we realized that the discovery was easy. Really, almost anything you did was new, and so we were able to generate a substantial amount of new knowledge into the properties of this element. I suppose the most fascinating thing that we've published has to do with the fact that these gold species form bonds to other metal atoms, unusual bonds, a new type of bonding actually called orophilic bonding, gold-loving bonding. And so that's occurred. Orophilic, yeah. And in fact, that discovery led to a lot of fascinating properties of these materials, and ultimately to a formal formation of metal-metal bonds between elements, such as in this model, a gold and a platinum atom are linked together directly by bonding. And that all has taken place since the middle 70s. Wow. Well, this obviously is a model of a molecule. And it's a clearly describable model of a molecule because the model tells us all of the distances between the various elements that are present in the molecule. We're able to do that today with modern computers and techniques. We're able to actually determine distances and angles and shapes and structure. And I've always been interested in the structures of things. But if we understand the structures of things, we begin to understand how the reactions occur, how a molecule can come in and attach itself at a given position in to a molecule that's already there and carry out a chemistry. In other words, materials like this can be catalysts if they can attach themselves to other molecules that might come into the system. For example, gold in medicine appears to attach itself to not only the cells in our body, but that contain sulfur, but also to oxygen, an oxygen-related component. Right now, the biggest fascination we've had has dealt with understanding how these gold compounds can lead us to new catalysts for chemistry and that is commercially available. In fact, we've been doing some very interesting work that suggests oxidation of olefins or carbon monoxide can be achieved starting out with molecules that we can make in the laboratory and then treating them in a given way to produce a gold catalyst that can be put on a surface. That's one of the things, and that's been a lot of fun because it's brand new again. We recently discovered for the first time that one can put two gold atoms at a very, very short distance, shorter than anybody had ever seen before in the world. What it translates into is that it influences the optical properties. In other words, light is absorbed differently with these sorts of molecules, and they might be used, and in fact, in some cases can be used for optical detection purposes, for devices, electronic devices. It's hard to predict exactly today what the materials will ultimately be used for, but it's exciting to realize that just because you've been able to find a molecule that has a given shape and structure, you can start suggesting new molecules that might be made that will have a better property, such as better phosphors for our TV screens, for example, or better colored materials for detecting the presence of molecules we don't want in our atmosphere environmentally. Well, I think the changes from the specific contributions we've made are difficult to predict, but I'm sure that people will have a much better appreciation for really the power of the chemistry of gold in a lot of different areas. And we're seeing evidence of that already in some commercial materials now that companies like Dow and others are using. First of all, I think the student generally knows I have a gold pin on, and we all use all sorts of gold in our jewelry activities. And why do we use it? That's one of the first questions. Why does gold well like this? And part of the reason for that is that it's not very reactive to our environment, our world. We can use gold on our fingers and on our hands, and it doesn't react with the chemicals in our skin. It's beautiful in that respect. Why? Well, because, of course, it's special properties that deal with the element itself and its interaction with the environment. Working with gold as an element, and I've worked with other ones too, but with gold you can talk about it to people. They know what you're talking about. And so you can excite students about it and even let your wife know what you're doing once in a while. Medical school students and veterinary school students and others need to understand the actual reactions in chemistry, molecular chemistry of drugs, obviously. And most of the time they learn that pretty well in terms of organic materials. But I've been a very strong proponent of the fact that our body is not made up of just organic materials. There are a lot of inorganic materials there. And our pharmaceutical companies, by and large, really don't understand that in some cases. It's sad, but for example, cobalt is in all of us, is a particular ion. Small amount, to be sure. Or nickel is in all of us in a very small amount. We know approximately what these trace elements do and why they're there, and we know that we can't live without them. But we don't know in many cases how to make the compounds that they're actually found in our body, and then how to control them. And so if you have a disease such as Wilson's disease, for example, which is a disease related to copper and the inability of your body to get rid of excess copper, which you get by eating, then you're in trouble. You're going to die. And so you need a drug that is going to be able to interact with that excess copper to remove it from your body. I've taught my whole life, and as I said very early on, I wanted to teach. I'm a distinguished professor, and some distinguished professors at A&M don't teach, but that's not true of me, and I enjoy it very much. I usually teach a graduate course and an undergraduate course each year, and sometimes I have been let out of one or the other of these courses, obviously, but I enjoy teaching the freshmen, particularly the honor students. That's a lot of fun. I like to golf, and I like to fish, and I like to read. Although as I get older, my eyes aren't as good as they used to be. Play with the computer a little bit, but really get outside and do outside sort of activities like fishing and golf. I think the first question that anybody has to ask is, what do you see about what you're observing that you might like to know an answer to? For example, the brown suit that I'm wearing, why is it brown? What causes the colors to occur? Why is the gold yellow? Those are the sorts of questions, and then I think if you can get answers to them, start probing on the molecular level, if you can, of what causes these things to occur. That's not always easy, but I think that grammar school students and high school students see a lot of things around them they don't ask questions about that involve mental ions in many cases. And if they started asking questions and got answers, I think they could develop an excitement about the science. We all are familiar with various aspects of what comes over the radio to us, and it's always surprising to me. Virtually every day there will be a comment made by a reporter or someone else that's scientific that is wrong, that is really incorrect. One of the problems we're talking about today is the transport of radioactive materials. And then people are talking about the terrorism possibility of somebody importing plutonium into the United States in small canisters. Well, that seems natural for a reporter to say that because, why not? Well, if someone had any plutonium at all and tried to transport it, any of the high purity plutonium, they would not be here. They would be dead because the radioactivity would kill them just in the transportation process. So those sorts of comments you hear in the radio periodically, and our society has not been educated very well in terms of asking questions about, is it really true that this plutonium could be carried in some sort of a container? Well, I brought this along because it really relates in a way to this. This, as I said before, is a model of a molecule. It's detailed structural information about a molecule. But in order to know what this really looks like, this model looks like, this molecule looks like, we recognize that we need to understand how X-rays interact with such a molecule. And X-rays take advantage of symmetry features. And this model I have here happens to be a model of it's a puzzle, really. I can take it apart. I don't think I could get it back together again easily, but if I do, but it's a puzzle. And these puzzles, such as this one particularly, have a lot of symmetry. This one has a sort of a relationship that looks like you could rotate it by a third of a circle, and it would be the same as you saw before. Well, this one not only has that type of a feature, but if you position yourself to the 4 positions of my fingers, that forms a tetrahedron. And so this overall structure is a very, very high symmetry called cubic. And it's that information and an understanding of that information that allows us then to deduce structures like this. Without one, we don't have the other. So this understanding of symmetry properties led us to the ability to understand molecular